Predicting a catastrophic flood is a deterministic mathematical process. It requires calculating exactly how water moves over physical terrain, second by second, without guesswork. To execute these calculations, hydraulic engineers use software like HEC-RAS to solve the two-dimensional St. Bonnot equations. These equations enforce the laws of physics, specifically the conservation of mass and momentum for a fluid traveling across a complex, uneven surface. But solving complex hydrodynamics is entirely useless without precise physical inputs. In flood modeling, the rule is strict: garbage in, garbage out. An inaccurate model misdirects emergency responders during a crisis. To be valuable, these models must output actionable, hyperlocal intelligence. We are going to construct a high-fidelity 2D flood model from first principles, mirroring the exact workflow hydraulic engineers use to predict extreme events. Accurately predicting a disaster requires synthesizing hydrology, topography, and hydrodynamics into a single pipeline. Mastering this sequence is a prerequisite for saving human lives. To build this simulation, we start with hydrology. In a mountainous catchment area, the first step is quantifying the exact volume of precipitation falling into the basin over a specific time period. A catchment does not behave like a concrete bowl. A significant portion of that precipitation never reaches the river due to hydrological losses, primarily infiltration into the soil. To mathematically subtract this absorbed water, we use the green-amped infiltration method. This physical model calculates the absorption rate based on the specific hydraulic conductivity and capillary section of the local soil. The water that remains on the surface after these infiltration losses are calculated is defined as effective rainfall. This effective rainfall is then routed down the natural slopes of the catchment geometry using a unit hydrograph. The end product of this phase is the direct runoff hydrograph, a curve plotting the exact discharge in cubic meters per second over time. This curve serves as the exact thermodynamic fuel. It provides the upstream boundary condition for our entire hydrodynamic simulation. With the water quantified, we shift to the physical arena, the floodplain. Gravity requires a hyper-accurate three-dimensional canvas to route that water correctly. Standard drone photogrammetry is insufficient. It generates a digital surface model, which wraps the tops of tree canopies and roofs rather than the earth below them. Feeding a surface model into HEC-RAS causes the software to treat a dense forest as a solid, impenetrable concrete wall, routing digital water completely in the wrong direction. To solve this, engineers deploy aerial LiDAR. The laser pulses penetrate gaps in the leads, striking the earth below and digitally stripping away the trees. The resulting output is a true bare earth digital terrain model. Both drones and aerial LiDAR suffer from a second topographical blind spot. They cannot penetrate the water's surface, which renders riverbeds artificially flat in the data. We fix this by surveying the river with sonar echo sounders and splicing that underwater bathymetric data directly into the terrain cross-sections. Fusing canopy-penetrating LiDAR with underwater bathymetry provides the physics engine with accurate channel capacity and an objective topographical truth. Topography dictates where the water flows, but the texture of the surface dictates how fast it gets there. To quantify surface friction, the software uses Manning's equation, relying specifically on the Manning's N roughness coefficient. Engineers generate a land-use land cover map by analyzing high-resolution ortho-imagery of the entire project area. The image undergoes vectorization, where distinct geometric polygons are drawn over forests, roads, and barren land, filling the map with distinct classification codes. Each polygon is assigned a specific Manning's N value. A dense brush floodplain receives a high friction value, like 0.15, while a smooth concrete channel gets a low value, like 0.015. This integration transforms a static 3D map into a dynamic geospatial friction matrix, directly controlling the velocity of the impending flood wave. The equations are calculated on a two-dimensional computational mesh, a grid network laid directly over the terrain. This presents an immediate computational bottleneck. Running a strict 1-meter resolution grid over 50 square kilometers produces millions of calculation points and will instantly crash most solvers. HEC-RAS bypasses this limit using a proprietary technique called subgrid bathymetry. Engineers use large, efficient 50-meter computational cells. Behind the scenes, the software extracts a single elevation volume curve from the underlying 1-meter microtopography, feeding it into the larger cell's math. It retains perfect knowledge of the tiny gullies hidden inside. This introduces a specific failure point. If a raised road bisects a large computational cell, the cell's mathematical average will artificially flatten the road, allowing digital water to pass through what should be a barrier. Engineers fix this manually using break lines. By drawing a rigid line along the top of the road, the software forces the computational cell faces to snap perfectly to the hydraulic barrier. Subgrid bathymetry and break lines are strict engineering workarounds. They allow solvers to cheat computational limits without sacrificing physical accuracy. With the boundaries, the mesh, and the friction set, the unsteady flow simulation begins, pushing the hydrograph's water volume through the mesh over time. The greatest threat during this phase is model instability, a condition where the underlying math breaks down and the simulation crashes. Physically, this occurs when water moves so quickly that it completely crosses a grid cell within a single computational time step. To prevent this, the software uses a mathematical governor known as the current number. It is a ratio of the water's velocity, multiplied by the time step, divided by the cell size. The golden rule of HEC-RAS stability is that engineers must meticulously balance velocity, cell size, and time step to maintain a current number near or below 1.0. Successfully balancing the current number allows engineers to simulate chaotic, high-velocity extreme events without mathematical collapse. The ultimate test of this two-dimensional model is simulating a catastrophic structural failure, such as the breach of a major hydroelectric dam. To initiate the failure, the model requires specific breach parameters. Engineers must define whether the failure is caused by water overtopping the crest or internal piping through the foundation, along with the exact formation time of the breach. Inside the RAS mapper interface, the digital reservoir violently empties into the 2D mesh, mapping the resulting trajectory across the downstream terrain. As the water travels, we observe flood wave routing. The geometry and friction of the floodplain naturally soak up and spread the water, attenuating the peak discharge over distance. Using this data, RAS Mapper generates a hazard index map. By multiplying the flood depth by the water velocity, it identifies structurally devastating flow paths. Evaluating pure water depth is a fatal mistake in planning. The hazard index is the true metric for identifying zones where homes and infrastructure will be obliterated by the force of the water. Once the physics are calculated, the narrative shifts from structural engineering to emergency response logistics. The ultimate deliverable of the entire HEC-RAS pipeline is the arrival time map. This map provides disaster response teams with the exact hours of evacuation lead time they have before the flood wave strikes specific downstream coordinates. It dictates exactly how long civilians have to clear submerged roads and evacuate low-lying basins before the water cuts them off entirely. The accuracy of that life-saving lead time is completely dependent on the strict, deterministic hygiene of the upstream hydrology and topography data. Mastering complex equations and subgrid modeling provides the non-negotiable